Welcome to the Automating Security Verification Workshop series using test suite synthesis and portable stimulus. This series will be presented by Adnan Hamid and David Kelf of Breker Verification Systems. The three-part series will be divided up as follows. Firstly, we'll have a look at some hardware security fundamentals before looking at security verification and considering why this is such a complex problem. In part 2, we'll review portable stimulus-driven test suite synthesis and look at why it is actually particularly good for security verification, before then looking at a security methodology that was developed by an end user of Breker. In part 3, we'll go on to show a simplified example of security verification using this methodology. So first, let's look at some hardware security fundamentals. So today, it is clear that there are a number of applications where semiconductor security is absolutely critical, including some of the ones you see here. The question is how do you make a semiconductor secure against all the kinds of vulnerabilities that exist? And how do you validate this level of security in these applications? So if we look at a system today, a software stack built on top of hardware, we can see that vulnerabilities can exist throughout the entire stack. And in fact, the lower down the stack you go, the greater the vulnerability for the whole system is. So it's absolutely critical that the physical hardware at the base of the stack can be fully trusted. Various capabilities can be built in the hardware to protect it from vulnerabilities. And we refer to some of these capabilities as the hardware root of trust, or HROT. These might include a trusted execution environment that protects various areas of the SoC from hacking, cryptography, secure boot systems, and other mechanisms that make sure the hardware is fully secure. Let's take a look at some of the vulnerabilities that can exist in hardware today. In an SoC such as this, you may have protected keys that a financial program might make use of, which normally can only be read through a crypto engine. A hacker might be able to get access to those keys and read them into some other memory cell, and from there, find out what the keys are and be able to access the financial software. The same is true of secure registers in a safety critical device, such as an automotive device, where a hacker can access, say, to the brake register and manipulate it, causing safety hazards. Accesses into secure regions in memory can also cause difficulties, as can malware inserted in the boot code of a system, which can affect the entire operation of the hardware. Access can be provided through ports that are unexpected, for example, debug or JTAG ports in a system, and even the power rails can be examined using side channel effects to understand different operations in the chip and figure out security holes. Trojans or malware can be placed in third-party IP or even firmware or FPGA fuse maps that can be used inside the system. So all of these vulnerabilities can create security flaws in hardware that can be used to affect the entire system. The focus of this workshop will be on protected regions and registers that can be used to eliminate many of the vulnerabilities that we've just been discussing. For example, critical functions on the SoC may be contained within a protected region for which access may be controlled using a secure monitor on the fabric. Similarly, regions in memory that contain critical information can also be protected using the same secure monitor. A good example of this is the ARM TrustZone technology. ARM provides in most of its processors the mechanism that allows for a trusted execution environment, a secure zone to be set up in hardware with its own operating system and a virtual machine in software that is itself secure. Trusted apps that operate inside this virtual machine can be accessed through a special functional API that's security controlled. Many of these hardware root of trust solutions comes down to a hardware access control mechanism that exists on the SoC fabric. A security policy control device is included as part of the fabric to provide this kind of access control. This device interacts with the different blocks and memory regions hanging off the fabric and runs access control protocol to ensure that the different masters and different slaves on the fabric are able to control each other in a very specific fashion. This actually provides a very highly flexible SoC architecture and still maintains a powerful level of security for the device. It's worth mentioning that the source for this diagram is an IEEE paper, System on Chip Platform Security Assurance, which actually provides an excellent overview on hardware security. So if we look in more depth at these access rules, they tend to come down to a number of access stages, and each one can be depicted with a security rules table. And this is in fact the method that the end user that we work with on this security workshop actually used in their system. And we will use this approach to talk about the methodology that Breker proposes to handle security. So now let's look at security verification and why this is such a complex problem. So security we would term as a negative verification problem. So let's revisit the example of the keys being run through the crypto engine. A positive verification problem is basically making sure that functionality is correct, i.e. the key can actually be read through the crypto engine. A negative test would be ensuring that the key can in no other way be read from any other part of the SOC. It's the negative of that positive verification functional test. Now this negative verification is traditionally very hard to deal with, as it requires an exploration of the entire search space of the design to make sure that none of the vulnerabilities that we've been talking about can exist across the SOC. This can be done manually, of course, but to do so requires the engineer to predict every single possible access of the security mechanism right across the SOC, including all the vulnerabilities we've discussed and more. This is obviously very complex and difficult to do. It's very error prone and requires hacker expertise. Formal verification has been proven at the block level a very effective way to perform this kind of verification. So formal verification is good at exploring the entire state space of a block and basically allowing the engineer to ask questions about the state space. If we look at how formal verification operates and imagine the state space of a design exploded across all the possible states and across all the clock cycles, then the way a dynamic system such as simulation or emulation operates is by looking at one particular path through the state space clock cycle by clock cycle. Formal verification operates by looking at all the state space in a smaller number of clock cycles. And what you're able to do is essentially ask questions of the tool. So in this case, we would ask the question, is there any way to access this protected key except through the port and the crypto engine? And the formal tool can go off and explore the entire state space and figure out if indeed that's true. So at the block level, formal verification provides a very effective way of handling this problem. However, the issue, of course, with formal verification is that it's capacity limited in that it has to store in its data structures the entire state space of a design. And this is very storage bounded as you start to look at larger subsystems and especially SOCs. So we can only run formal verification on relatively small or medium-sized blocks. So what we would propose is a semi-formal way of looking at the system. If we can understand at a high level the complete search state space of the system, all the different blocks that can access the keys and secure registers, and all the different blocks that can read their output, and under each one of these blocks include all the mechanisms for actually how those blocks operate. And we can explode this in a system that allows us to walk all the paths in this graph. Then we can use this notion of exploring a state space of the design, but actually use it to generate dynamic tests for simulation and emulation and solve the security problem at the system level in this manner. In part 2 of this workshop series, we'll discuss test suite synthesis driven by portable stimulus and look at why it's particularly good for security verification. Then we'll go on to look at a proven security methodology developed by an end user of Breker. Thank you for your time.